Okay, so eventually this talk is going to be about high-dimensional expanders and certain types of concentration bounds, but I want to start way back before high-dimensional expanders existed with a very simple problem that hopefully will eventually lead us to high-dimensional expanders, which is the following. Can people see the top of the board here? So let's say we have a randomized algorithm. A for some decision problem, like maybe we're trying to test primality or something like this, and it has 2/3 success probability. Go with 2/3 success. And the question is very simple. I'd like to amplify the success of this algorithm, but I would like to do it without using too much extra randomness. And so what do I mean by this? Well, there's obviously a naive way of amplifying the success of a randomized algorithm with 0, 1 Boolean output with 2/3 success probability. I just repeat it k times and then I take majority, right? And standard concentration or Chernoff should tell me that the probability that I'm going to be, my successes are going to be way off from the mean should decay exponentially. So I should be able to exponentially amplify this, but I'm doing this at the cost of using a bunch of extra random, right? So sort of naively, if we start with, say, A uses like n random strings, this sort of naive amplification will exponentially blow up the amount of randomness we're using. This will go to like roughly n to the k total random strings. And to start, we'd sort of like to ask, can we somehow do better than this? Okay, that's the basic question. I want to give you sort of a combinatorial viewpoint, be a little bit more concrete about what I just said and what it means to sort of succeed in this type of amplification, and then how we would de-randomize it. Okay, so for simplicity, instead of actually independently drawing k random strings, I'm just going to pick a random k-tuple of random strings. So I'm going to assume for simplicity that I'm not repicking the same random string, and I'm going to draw this as sort of a hypergraph. Right, all possible sets of k-tuples are going to be hyperedges on the set of vertices 1 through n. So let me draw this over here. Here I have n, and up here I'm going to have n choose k, which we can think of as hyperedges in this hypergraph, but I'm drawing it in sort of a bipartite fashion.
Like capital N is like to the little and like the number of random bits.
Right. Yeah. So maybe I should have said we're using like if we're using n random bits, then we think of n as being to the little n, the total number of possible random strings. So here this would be n to the k, and in this world this would be sorry, what would, no, 2 to the n times. Right, sorry, number of random bits would be n times k.
So I'm just a bit lost. So we have an algorithm. If you run it once, the success probability is 2/3.
Yeah.
So you're saying now we're going to run it n times?
K times.
K.
I'm going to amplify this to some. Say I want to have success 1 minus delta.
Yes.
I'm going to run it like log 1 over delta.
Right. So that's k.
That's k.
And what is big N?
Big N is the number of random strings that this algorithm. This algorithm is pulling randomness from some universe.
Yes.
N is the number of random strings that it's
One run of the algorithm.
One run of the algorithm.
So this 2/3 success probability is generated by little n random bits.
Yeah.
Yes.
Okay.
Yes.
I'm with you.
Yes. Yes. Thanks. Okay. So the point is what property of this? Sorry. So I should say if this guy is standing for V1 through Vk, I'm going to draw a bipartite graph here by connecting this to V1 through Vk on the bottom, right? V1, Vk, and this is sort of connected by its inclusion structure. Okay, so the property that I'm actually using is the following. I say, take any subset of the vertices and think of this as on some particular input, some number that I'm checking. This is the set of random strings on which the algorithm succeeds. So in this case, I guess it's about 2/3 size, but imagine it's any set. The property that I'm using is the fact that when I draw a random k-tuple, when I draw a random vertex from this side of the bipartite graph, and then I look at the density I look at the fraction of edges that hit the successful set A, it should be close to the mean. with really high probability. That sort of a random vertex here should sample this set very well, right? And this is Chernoff's bound, so, or Chernoff Hopking, I guess. So this would say, you know, here's the actual property I'm using. The probability over, you know, S over S drawn from n choose k. So this is a k set of vertices, that the expectation over vertices in S, so this is just the expectation over its neighbors down here.
There's some in S, sorry, good.
In S, yeah. The expectation of this set, and this would be true for all subsets A, that the, you know, local expectation, that the density within A, you know, minus the actual global density of A is greater than epsilon, is at most, you know, something like e to the minus epsilon squared k. Right, so in particular, even if my algorithm succeeds only with probability half plus epsilon, Chernoff tells me that I'm still likely to see at least half of the correct answer with probability like e to the minus epsilon squared k. Okay, but hopefully also in drawing this graph, you know, sort of what I showed over here should, you know, become very clear. I started with n random strings and I've massively blown up, you know, the size of the randomness that I'm using to this complete hypergraph and choose k. And the question becomes, you know, more general than just amplifying the success of an algorithm. You know, is it possible to somehow de-randomize this sampling or Chernoff property? Can I replace and choose k here with some very sparse collection of k-tuples, some sparse hypergraph that still has this property that with very high probability, hopefully with like exponentially decaying probability, when I sample a k-tuple for any possible adversarial A, I see A in the right proportion. Right, so I want to somehow replace, you know, and choose k with some sparse hypergraph x of k, such that this still holds. You know, when I replace this with x of k, I get the same guarantee. And then, you know, I could do this amplification using hopefully many fewer random bits to generate xk.
Just one thing, I think like the setup you described probably corresponds to n to the k, right? Not n choose k, but you.
Yeah, so right, I'm for simplicity.
N choose k.
Yeah, for simplicity, I'm not allowing repeated
Yeah.
the same random string. I'm drawing a k-tuple. Yes, sorry. Technically, this would be like n to the k, which you could do over here, but it's going to be simpler to work in sort of the non-partite setting for the rest of this talk.
There's still a hefty inequality for sampling without replacement. It's not.
Yeah. This is you know, sampling for negatively correlated random variables instead of But thank you. Okay, you know, let me say, like, maybe you don't care about sort of this problem of de-randomizing amplification. It's important in a lot of contexts, but you know, we'll see somewhere soon, you know, this type of structure where I maybe want to repeat something k times and amplify some property. Like maybe I start with a weakly hard problem on n vertices, and I want to repeat it n times and take XOR, like an XOR lemma, or I want to use like parallel repetition or something like this. This all relies on similar types of properties. And here, you know, I really can't afford blowing up the size of my problem from n to the k if k is, for instance, super constant. Yeah.
So for this, are you saying you're just interested in getting a sampler, or are you interested in something else beyond?
Yeah, so for the moment, this is called a sampler graph. And I am just asking, do there exist sparse sampler, like averaging samplers? That is what this is equivalent. Okay. Yeah.
How sparse are you looking for?
Yeah, so you know, hopefully we would want, instead of this being size n to the k, we would hope that this is like maybe n times OK of 1. Like we would like to only have a linear number
I
of
thought that was
hyperparameters.
known.
It is known. I'm building up to things.
Okay, I understand.
Yeah, so I mean, if we want to jump ahead, the answer is you can do this with expanders. But you know, eventually we're going to want concentration properties beyond just this, and then things will become not known anymore. Yeah, so this is very known. There are many. I mean, these are samplers or seeded extractors. They're extremely well studied. They're very, very useful in pseudorandomness, cryptography, complexity. I'm sure many of you have seen or even used these options. They're really, really useful. But I wanted to start at a very basic level. Okay, so you know, my next question was, can we do this? We know the answer is yes, but you know, question, you know, can we find sparse X satisfying this. Okay. Right. So the answer is yes. And we're going to use this, beautiful theory of expander graphs. And I know that most of you are very familiar with expander graphs, but still I want to take a moment to make sure everybody is on the same page and go back over this. So okay, so what is an expander? Roughly speaking, an expander is a sparse graph so think of every vertex as having a constant degree, it maybe sees 10 other vertices, and yet in some sense, it's pseudo-random in that it acts like the complete, it acts like the complete graph. It acts like it has all edges in terms of connectivity properties and things like this. And I would encourage you to think of this as almost sort of solving the two-dimensional version of this problem. That we're going to build sort of graphs which are sparse, but pulling a random edge, or the k=2 case over here, acts like I've pulled two independent vertices. It's sort of pseudo-random against functions on the vertices. So I'll formalize this, but I want you to think of it as sort of being, pseudo-random again of functions of vertices. Okay, so let me actually define these objects for you and then be a little bit more clear with what I mean by this. Which we'll come back later. So there are many ways to define expanders. There's sort of combinatorial ways and spectral ways. For the purpose of this talk, we'll only focus on spectral definitions of expansion. So let's say we have this graph G. Let's assume for simplicity that G is regular. So it doesn't actually have to be the case, but it simplifies things somewhat. So if G is regular, then it's symmetric and stochastic, and so its normalized adjacency matrix has eigenvalues between 1, first of all, it has a spectrum, and it's between 1 and -1. So, AG has eigenvalues. So the first eigenvalue is always 1, which corresponds to the constant function, because it's a stochastic matrix. And then, down to the smallest eigenvalue, lambda n, which is most -1.
This is a normalized.
This is the normalized adjacency matrix. Yeah. So every entry will be, 1 over degree if between V and U, if there's an edge between V and U. And we'll say, so slightly, we'll say definition that G is. So G is a lambda expander, or really a one-sided lambda expander. If the second eigenvalue, lambda 2, is upper bounded by lambda. So basically, if all non-trivial eigenvalues are small, and this is one-sided.
It would be good if you write bigger.
Right, bigger, okay.
For the audience, but then it's recorded and people will look at it.
Okay, I will write bigger after this,
Yeah.
this definition. One-sided. There's also the notion of two-sided expansion. Which says that the maximum of lambda 2 and the absolute value of the smallest guy, so this is, we want everything in absolute value to be small, is less than or equal to lambda. Okay, so this is the spectral definition. This sort of spectrally mimics the complete hypergraph, right, which has eigenvalues like 1 and then 0 and 1 over, actually I guess just all 1 over, -1 over n, number of vertices. Okay, so that's the first definition. And the second, I want to give you sort of this, what do I mean by it being pseudo-random? Which we'll then, use later in the proof when we're actually looking at these things. So definition 2, which is sort of the pseudo-randomness definition, says, I want to sort of draw, I guess people would call this the bipartite cover. this graph where these, if I have vertices on left and right, and I'm going to draw an edge between x and y when there's an edge in the graph. What?
Yeah, okay, it's two edges, right, between y and x.
Yeah, right. There'll also be x and y. There'll be another edge there. What I want to say is that if I have sort of a function f on this side mapping vertices to the reals, and I have another function g on this side mapping vertices to the reals, that this graph is pseudorandom in the following sense. If I take the correlated expectation of f times g across an edge in this graph, so the expectation across these pairs, x, y, that are in E of f of x times g of y, this should act like I had sampled these independently. That this we can sort of decorrelate these these edges. So this should be approximately the expectation of f times the expectation of g up to an error term that scales in lambda. So plus or minus lambda times the square root of the variance of f times the variance of g. So this is what I sort of mean by this, graph is pseudorandom against functions on the vertices. That when I take an expectation of f times g across edges, it acts like expectation of f times expectation of g. And this is equivalent to the above definition, and we'll actually use expanders in this way later on in the talk. Okay, I guess the last thing I should say is that these objects actually exist. Right? That I guess we've known since 87, and sorry, not 87. Earlier, right? When was Margulis? 73?
73.
Yeah, so we've known since work of Margulis, that roughly speaking, there exist lambda expanders, explicit and strongly explicit, I guess, constructions of lambda expanders, maybe for like infinitely many number of vertices, and of degree, roughly like 1 over lambda squared. Theta. So, okay, I'm not going to worry too much about exact dependencies, but the point is, if I want sort of a constant expander, I can strongly explicitly build a constant degree graph that has these properties.
I guess next week we'll hear about random graphs.
Oh, good, yeah. So in this case, we're trying to de-randomize, so we'd like things to actually be explicit, but it's of course very interesting to understand to what extent random graphs are expanders, things like this.
So strongly explicit, you want to explain what it means?
This means you should be able to generate if you give me a vertex, you should be able to generate the neighborhood of that vertex in logarithmic time or polylog.
Polynomial in
the name of the
Right, polynomial in the name of the
This is
vertex.
important because capital N there is an exponential.
Right, is to the little n.
You really want to.
Yeah. Okay, so how am I now going to take these sort of two-dimensional pseudorandom objects and sort of amplify them to solve this k-dimensional problem? Well, here's a very beautiful theorem, an idea originally due to Ajtai, Komlos, and Szemeredi, and then optimized by Gilman, which is just to take paths on the expander. So if two things are an edge is sort of pseudorandom against two, I'll take a k-length path of vertices and hope that this sort of generating k-tuples in this way will still be, still remain pseudorandom against functions of vertices in this sense. So here's a theorem. We'll call Expander-Chernoff. And Gilman. Sorry, this is 87. This is maybe 88. So this optimized version that I'll write is due to the later work of Gilman. And it says that expander walks have exactly this property. That in particular, you know, if xgk is the set of length k paths on a lambda expander G, then this probability above, you know, for all subsets A, so say this is, you know, the vertices of G. G is on, you know, vertices 1 through n, match what we were doing above. Then for all subsets of the vertices, the probability that a random path sampled, you know, from this hypergraph, that, you know, exactly what we wrote above, that the local expectation of A on this path, you know, picking a random vertex from this path, A minus the actual expectation of A is greater than epsilon, is at most something like e to the minus 1 minus lambda epsilon squared k, I think, over 4. Maybe the constant doesn't really matter here. But the point is that,
Sorry, what is mu, the mu A?
this is the density of the set A.
Okay.
Right, this is saying like we expect to be hitting A, you know, in the density.
It's just some constant density.
Yeah, think
Or whatever.
think of A as being technically here. There should probably be some dependence on the density if you really want to optimize it, right? And Chernoff there is, but think of it as just as constant for some.
It's just the average of the indicator over the entire set N, right?
Yeah. This is sorry. This is just the expectation of A over N. Thank you.
Of the indicator.
Yeah. Yes, thank you. Right, so this is just saying the local, you know, the probability that the local expectation is off by more than epsilon from the global expectation still decays like e to the minus epsilon squared k up to this constant dependence on lambda. Okay, so this is a very beautiful theorem, and, you know, combined with this fact of there existing strongly explicit expanders of degree like 1 over lambda squared, then, you know, this sort of implies a solution to this problem where the size of xgk, let's just set lambda to be some constant, is, you know, n times 2 to the O of k. And up to worrying about the constant here, which is important in some applications because it's in the exponent, but up to worrying about the constant, this is essentially optimal. I don't really know who first proved this. It's in this work of Kennedy, Evan, and Golderreich. I'm sure that people will observe this earlier, right? If you want to have concentration that's exponential, you need exponential degree. It's not all that hard to show that. Yeah.
Sorry, and just to check, so S is uniform among the paths.
Yes. So S is I pick a random vertex and then I take a random walk. And why is this 2 to the k? Because it costs me n, you know, n guys to pick the first vertex. But now at every step, I only have a constant number of things to choose from. So I pay, you know, some 2 to the O of k.
What did you just say about the degree? You need exponential degree.
No.
No. When I take a path of length k, each step is constant. So
Yes, right.
it's constant to the k. So there's just an exponential number of these. And oh, you mean what is?
You just said something I didn't.
Yeah, sorry. I meant that the size of this has to be n times something exponential in the dimension. This has to be, you know, the number of paths. You can't hope to sparsify this much further and maintain concentration like e to the minus k.
But you could do much better
So
over there, right?
But
Because you
N
can-
times D to the K is what's going on.
Yeah, it should be n times degree to the k. Yeah.
But then you're also claiming that's essentially. Yeah.
No, what's written.
I'm ignoring the constant in the exponent, right? You can there's a lot to play with in the constant in the exponent. I guess this shows up in coding theory and rates, and like this is a very important
Okay.
point.
But what you wrote there is not optimal, right? I mean, you can have a 3 regular graph that is little O1 expander, so.
It should-
Regular outcomes is not 0, 1, and there is some constant.
if you take a random three regular graph, then the second eigenvalue.
But isn't that all-
It's
two- wait, yeah, what is-
That's true, yeah. So you don't, no, you're right.
But I think maybe high level, for people who didn't see it, I know most people have seen it. You should imagine this Gilman results, or the original one with Boas constant, is sort of amazing because a walk that is highly dependent. I mean, the sequence of points you pick one random point, and the second point has just a constant amount of randomness in it. It's a neighbor, and then so is the next one, and so is it. It's very constrained, behaves just like a random walk and a complete graph, like something independently, and they basically no change in the exponential behavior. I find it remarkable, even though the proof is not so complete.
So yeah, given that we've stopped, I want to maybe ask one question, Max. Yeah. So, this is about preserving expectations of linear functions of k bits. Yeah. If I wanted to ask a version of this result for, let's say, quadratic polynomials, is there something? Yeah, so it's going to depend also on how we phrase exactly what a quadratic polynomial means.
Okay.
You can then start using like hypercontractivity or other things to get bounds.
Okay.
Most of this talk will be about a version of that question, except it's not quite going to be polynomials in that sense. But indeed, where we're going with this is the fact, okay, thank you. This is the right segue, which is to say one way to view this bound is to say that expander walks are sort of pseudo-random against degree 1 functions. And I'll sort of view this as functions of the vertices of this hypergraph. So it's going to be a little bit different than the polynomial question. But indeed, in modern applications in complexity, we often need concentration of these derandomized objects against much broader classes of functions. We want them to act pseudo-random, not just of functions of the vertices, but maybe functions of edges or triples or I-tuples within this set system.
So I just want to say, I just take it back. It's just written inversely from what I'm used to seeing. So
yeah.
if the degree is d, then lambda can be 1 over square root.
Yeah, yeah,
This
yeah.
optimal
Yes,
binomial function.
it's the one below, yeah.
That's what I thought you were
Yeah.
talking about.
It's written backwards.
So it's written
Yeah.
backwards, so it's
Yeah,
hard to
you need to have
read.
some time.
I thought this was the cross-cultural part of the talk.
Okay, yeah, so what we'd like to ask is, can we build derandomized systems exactly that are concentrated against, in this case, functions of edges, I-tuples, etc. And that's really going to be the main question. And indeed, this type of concentration shows up in particular in hardness amplification, which is sort of this one other type of amplification that I mentioned earlier. You really need concentration. Chernoff is not enough. You really need concentration against these more general classes of functions. And I'll try to actually explain to you where this comes up and formalize exactly what I mean by concentration against I sets versus vertices. Okay, so I'm maybe gonna erase this. Still work here. Okay. So we're going to redraw sort of a similar version of this diagram, but instead of just having this k uniform hypergraph xk at the top and vertices at the bottom, we're going to include all size subsets in this diagram. Okay, so I'm still going to have xk, which is some k uniform hypergraph on n vertices, just like it was above, and I'm going to have the vertices. But now I'm going to include sort of this center level xi, which is given by downward closing the hypergraph. So for every k set, I'm going to include all of the I size subsets that are inside that k set in xi. So this is just the downward closure of the hypergraph. And we're dealing with these things distributionally, right? I'm talking about the probability over something from xk. So how is this actually generated? In a literal sense, I will think of the distribution over xi as being, one, I draw a k face, v1 through vk from xk, and then I uniformly at random subsample I of these vertices, and that will generate xi. And we can also think of, n down here as this, right? If the hypergraph is regular, I can generate the vertices by randomly picking a hyperedge and then randomly picking one vertex out of the K. So all of these levels xi are generated in this fashion. So pick, random t in V1. Sorry, I should draw bigger. Vk of size I. Okay. And now, the question that I want to ask before we had some set, A that was sitting down here, and we asked what's the probability when I draw a K edge that I sample this set A correctly? And now I'd say I want this not only to hold for vertices, but if now I take a subset of things that live on I sets, that live in xi, and sort of morally, you can still think of this as a degree I function, but it's not quite a polynomial in the sense that Ravesh was talking about. There's some Fourier analytic way to think of this as a degree I function, but I don't really want to go into it in this talk. But we want the same guarantee, right? We have some A. I've told you how the edges of K versus I are drawn here, right? This is connected to all of its subsets. And I still want the guarantee that with high probability, the fraction of these guys that sample A should be close to the mean of A. So let me draw out the guarantee that we want. It should mimic, this guy above again, but now we're going to have for all A that live in xi instead of x1, the probability over S being drawn from xk. Now we have the expectation of T being, instead of a vertex, we're now drawing an I set from S of, 1A minus, I'll still just write mu of A, but this is the global expectation of A. Sorry. We had the probability that this is greater than epsilon is at most something.
I don't understand what you're writing here. Xi is an instance, right?
X.
You mean for all A
is a subset. Yeah.
A that are subsets of n choose I?
Yes. Well, not n choose I. These right. Xi is only the I tuples that appear in this hypergraph.
So xk is no longer n choose k, it's some.
This is some K uniform hypergraph. That's a subset of n choose K.
You are trying to mimic n choose I though, right? Yes?
Well, if you have a very sparse
No,
xk.
The test is trying to.
Yeah. The test will be mimicking n choose I. Yeah. But like you'll be very far from having, there are n to the I possible I tuples, and we're only going to have n times like 2 to the I or 2 to the poly I of them. So right, in terms of density, it'll be very far, but we are trying to mimic the behavior of a random K set and a random I set. So is that?
I guess the statement doesn't change if you say for all I and n choose I, right? Because the indicator of A will just be 0 if you draw something that's not there, but it doesn't appear in the probability.
Yeah, that's true. I never thought of that. Yeah, so I guess you could write that because it would just be a 0.
Maybe
Yeah.
it's also important to understand that mu of A is it's with respect to a certain distribution on.
Right, in particular, it's this distribution.
Yes.
Right, that I'm measuring A by drawing a K set and then drawing a random I set. What's the probability of being in A?
It seems strange because originally you introduced these expanders as a mechanism to draw from n, right? And n is a defined independent of the structure of the expander. But now
Yes.
the definition you're making
Yes.
depends on the structure of the expander.
Yes.
It seems, well, why would you want?
So let me, the next thing I want to do is tell you why this is a reasonable
Okay.
definition. Because I also, and part of the reason this does not look like sampling polynomial is exactly because of what you've said. This is why it's sort of not, unless this is really like complete or looks like the hypercube, in which case it is sort of like sampling a polynomial. Here it's not. It's something else. We've done some sort of derandomization of sampling polynomials, but it's not the same. So let me try to justify why you would want this type of concentration. And it's going to come back to yesterday's talk, or a combinatorial version of yesterday's talk in agreement testing, in these types of local tests, which is where this type of structure shows up in hardness amplification. Okay. So I'm going to take a brief sojourn into the area of agreement testing. And this is like a combinatorial version of the low degree type tests we saw yesterday. So this is often used as a core component, and we'll sort of see why in the amplification and construction of PCPs and in general in hardness amplification, XOR lemmas, things like this. Okay, so what is an agreement test? So we're going to have some universe which you still think of as n. The fact that I'm drawing it as a grid does not mean that it has any structure. With apologies to Avi, it'll just be easier to draw some things on it. So I have some universe, and I'm going to be given a collection of local assignments on this. So sort of for every, we're going to be given a collection F, which for every k set of these vertices, we're going to go back to being on the complete case, but we can see how it'll generalize when we look at not the complete hypergraph. So for every S in and choose K, we're going to be given this local function, Fs, which maps the vertices in S to F2. So basically, over all this, maybe I have k equals 4, and we'll do this in red. And here's a local hyperedge, and I'm given a 0, 1 assignment to these local vertices. So 1, 0, 0, 1. And the point is, I would like to test whether these, this collection of local assignments is actually the restriction of some global function that's sitting on my universe. I would like to test if, f of s is actually coming from some function, some global function g. Right, maybe g, has some other values up here, but, hopefully the values I'm seeing here are actually just the restriction of this function g. Right, so we're trying to sort of test, is f of s equal to the restriction of some global g on this k set S. Okay, why am I doing this problem? Morally, the setup is that I'm starting with some maybe weakly hard problem on this universe N, some CSP or something like this. And I'm trying to make it harder by repeating it k times, by making you solve k instances of this problem in parallel. So these local f of s's, these are solutions to the k-wise problem. I'm giving you a challenge of sort of k things, and you're telling me the k solutions to these challenges, to these vertices. And why am I testing this? Because I need to make sure that when you gave me this k-wise sample, that it actually corresponds to a solution to the original problem, right? I need to somehow maintain the hardness of the original problem to amplify it. So I need to test that, in the PCP case, the provers aren't cheating and somehow using, k-tuples that don't actually correspond to a direct product of the original instance. And I do this via these types of agreement tests.
It may be useful to draw another force set on which the function was different than the initial.
Yeah, okay, good. Yeah, so maybe there's a force set here where in fact, this is 0 and this is 1.
So you want to intersect the other one.
Okay, I was going to do that up there.
Oh, okay.
Yeah, I'm about to do that. So
Okay.
good. So how would you actually test something like this? What Avi is saying is that really the only natural way to do this is to draw some, k sets that intersect and check their consistency, to test them on the intersection. But maybe first, let me actually say sort of slightly more formally what you want out of this test. Right, so really what you want is, we want to build some test that sort of only looks at O of 1 k sets. We want to only make a constant number of queries, right? This sort of number of queries was what Prahlad was talking about yesterday. That's so important. So we want to make sort of O of 1 queries, which just means I'm only going to look at the function values of, a constant number of k sets. Then, these two properties, we want completeness, which means that if this f is actually coming from a global function, this test should pass, right? So if f is global, this test passes, say with probability 1. And 2, you want soundness, which says, the opposite. If the test passes with some reasonable probability, you want to infer that f is somehow close to a global function, right? So something like, if probability of pass is greater than delta, we hope to show that this implies that f is like O of delta close to a global function. Okay, I'm not going to go deeply into exactly what this means, but think about it being as there is some global function g on which it almost agrees with it on a delta fraction of the domain. something like this. It's, close to delta global. Okay, now let's do what Avi said. How are we possibly going to do this? Really, the only natural way to do this is to draw some k-sets that intersect and check their consistency. Right, so in particular, the simplest version of doing this is I'm going to draw two k-sets, S and S prime, that intersect in T, and let's say that we fix the intersection size to be size I, and we say, test passes if, f of S on T is equal to f of S prime on T, right? We just check their intersections across this graph. Okay, now my claim is that this should remind you of what's going on over here. In particular, if we were to do this, nothing that I said in this particular test really relied on the fact that I was looking at all of the possible hyperedges. I could have defined this type of test for any, hopefully derandomized hypergraph. So maybe let me say, when we're looking at the scenario of trying to amplify the hardness of a problem, if we use n choose k, we're really blowing up the size of the problem from n to n to the k. And if we want to, say have k be super constant to get subconstant soundness PCPs, then we can't do this up here because it would blow the size of the instance beyond polynomials. So we'd like to find derandomizations of this that will work. And the claim that I want to say right now, which I'm not going to formally justify since it would take another 2-hour talk to do, is that somehow the best possible soundness that you can get here, right? Like we'd like this to be true for the smallest possible delta. This will correspond to sort of how much we get to amplify the hardness of these problems. And I claim that sort of the best possible delta that you can do when you do this sort of k versus I versus k test is very strongly related to the type of concentration that you see on this k versus I versus k diagram over here. So this is sort of where this type of thing comes up. These diagrams come up as sort of the consistency checks of amplified PCPs or problems in hardness. This is why we're interested in this sort of structure rather than trying to sample all I sets or something like this. Yeah.
So is like one direction is if it's not an expander, it's not a good sampler, then this can't work.
I don't know. It should, that should be the case. I'm trying to think I don't know if there is a very formal way. Actually, I think there is a formal way to say if your object has non-expanding local parts. I think this was proved by, do you remember who it was, someone remember who it was proved by?
They got two global functions and you don't have a lot of checks between them.
Two global functions and the two different parts.
Oh, right, yeah.
I mean, for the graph case, it is obvious, right?
No, I think that if you have something that has its test and then you add just a tiny component
right
outside, then technically it won't be an expander, but still
it would still work because you only
but you could probably formalize something.
There's definitely some version.
There are supposed to be silly counterexamples, but maybe.
But the intuition is what Arid said. If it's not expanding, but okay, what's not expanding? I guess right. The test graph, I guess, is what you were saying, right? Then you can have sort of some disconnected-ish components, and you can put different global solutions on. But as Yotam said, maybe one small. And, okay, so morally the answer is yes, but maybe formally it would have to have some quantifiers to say.
Max, can I ask you naive questions?
Yeah.
So now your new problem here, A is a subset of this xi.
Yeah.
Not just some set, right? Rather than having the set n, you now have xi. So why can't you just build a new expander on xi? Who cares about xk? I'll just take xi, it's a set of a certain cardinality, stick an expander on that and sample from that.
It's more expensive.
So the question is, how much more expensive? This is what I'm trying to understand.
Well, I think-
What do we want
No,
to
it's
pay?
not. It said it won't correspond to the structure anymore.
That's right, so I think that he was giving an exposition in one way, but now he's actually, his remotivation is slightly different. It's more like, here is xk, we care about it, we have a subset of xi, that's what we care about, and now we will solve this problem, so what you're troubled by is the exposition is not perfectly suited to the theorem.
I see.
Yeah, this
So
is.
if we really just wanted to sample, right here, get a good approximation of sampling for indicator A, what I said.
Would be.
Yeah, there's no reason not to do it. Yeah.
I
It's
see,
just that we really care, like this is coming from some agreement test that we want to
I
analyze.
see.
So we really care about this k versus I structure because it's coming from this. If you try to change it, it will no longer be about this k versus I
By the way,
structure.
as far as I'm concerned, the agreement test is a very nice application, but really, you have this X, it's a simplicial complex with k dimensions. And you want to sample the I-dimensional faces. That's a valid without the agreement testing application.
I agree. I think this is a reasonable question, but I guess you have to be convinced that it's reasonable to look at the simplicial, why would you look at the simplicial complex corresponding to xk and not some other object that's generated by, in the paths version, maybe I shouldn't be taking all I subsets. I should be taking,
I'm saying something else. I'm not even entertaining the question why. I'm presenting this as a question. If you want to entertain the question why, then you need to say, oh, I have these applications. But you might say, it's a natural thing. Just like in a graph, I want to sample functions on the vertices. In a complex, I want to sample functions on the edges, or maybe functions on the triangles. To me, it seems natural, I guess.
Okay, Arit's trying to help me, so I shouldn't fight her. No, I totally agree. And, I was interested in this question as a, probability and simplicial complex question versus, of course, Yotam and I were motivated by agreement test when we looked at this, but I was very interested just in understanding these concentration properties sort of beyond vertices in a hypergraph. Okay. Yeah.
Can I just have one more comment? That I think this question is even natural when you set I to 2. And you're probably alluding to this eventually, but you can ask, suppose I don't have a function on the vertices, I have a function on edges of the graph that I care about. Now the edge set is important to me, even if it's not all n choose 2. And still I maybe want a way that sort of also corresponds to using the graph to sample functions on the edges. You can ask if long paths would sample well functions on the edges or not. And I think there are many legitimate reasons to sort of try and consider these intermediate sets, even if they're not all of n choose I or something like that.
But the Harmon will tell you build an expander on the edges.
No. Maybe you can do that, but I can also ask, right? Why do I need to build an extra expander on the edges? I already have my existing expander on the graph, and I know how to sample from that by long paths. Does this work for edges too?
It's a perfectly legitimate question. I was just trying to match it with the motivation.
Yeah, no,
The original motivation had no structure, right? It was just n. And you just designed an expander just to sample, right? And my question was, why can't you just do that here?
Yes. Totally valid
Of
question.
course, if you already had a graph structure on n, what you were doing originally doesn't make, you can ask the same question originally. What do I do with my given graph structure, right?
Right, yeah. And I guess in these applications, we do have a given graph structure coming from the test that we care about. Yeah, thank you. It's a good clarification.
But
Okay.
I agree, this is a natural question.
So I want to jump back to here and ask, what should this question mark value be? Even when I, look at n choose k, because the idea here is generally, as Xander was saying, we're trying to de-randomize the properties of taking all possible k-tuples. So the first thing that I should understand is when I replace this with n choose k, what is the right bound here? This is I don't think this is immediately obvious. As far as I know, this bound was first given in this paper of Impaiazzo.
So just now, xi is the set of all subsets of size I or a subset thereof? What is xi now?
Xi is all, sorry, in the case of n choose k. Yeah, so it's generated by picking, a random k-tuple from this, which is a random k vertices, and then subsampling I of them. So this just uniformly at random. So this is exactly all I sets in this case. Yeah. So when you're complete, these are all, this is n choose I, this is n choose k, this is n choose I, and this is n choose 1. Yeah. So it will look like that in the complete case, but when we de-randomize, it won't, right? It'll correspond.
My point is that the restriction to a smaller set of hyper edges only appears at the top level xk. Once you go to xi, you pick all subsets of size I of the hyper edges in xk.
Yes.
Yeah, that's the definition of a simplicial complex.
Yeah.
You take a hypergraph and throws it down.
Yeah.
Okay.
Cabinets and I and Gunderson. And this was exactly in this context of agreement testing and the construction of PCPs. Maybe this was done earlier as well. I don't know, Avi, if this is the first place I've seen it.
This is not complicated.
Yeah, it's not too complicated, although it takes a second. I don't know, does anyone who doesn't know the answer wanna posit what we should write here? Should be some, dependence on K and I.
So it's not completely obvious.
It's not, yeah, okay, this is the point I'm trying to make. Somebody would say if it was completely obvious. It's K over I. And why? Okay, morally. This is because, how do I get this bound? Well, I view a K set, right, V1 through Vk. I can sort of try to view this, especially in the case of n choose K, if n is, think of n as being way, way larger than K, so there's very little dependence between these. I can essentially view this as, V1 through Vi, and then Vi plus 1 through V2i, etc. I can split this into essentially, K over I independent I sets. So they sort of live, in this universe, K over I independent variables. And then I'm going to apply Chernoff to these K over I independent variables and get e to the minus epsilon squared K over I. Right, so this is like K over I roughly independent K sets. Sorry, I sets. Okay, you should maybe be a little bit troubled by this intuition because, I've randomly partitioned the vertices and I've said these are independent, and Chernoff then tells me if I pick one of these random partitioned elements, I'll get, e to the minus K over I concentration, but that's not actually the graph we're looking at, right? We're not picking a random partition, we're picking a random subset, but you can argue that at least on n choose K, these are close enough. And in fact, you can actually argue, which I think we won't have time to cover, that, the concentration of this graph is never much worse than picking a random partition like this. This is sort of why you get e to the minus epsilon squared K over I. And then maybe the other thing that you shouldn't yet be convinced of is that this is the correct answer. And I just told you this is why you should be able to get this answer. But indeed, this is tough. So you can prove that the concentration is, no better than e to the minus O of epsilon squared K over I. And I'll just say the example, the counterexample, and I won't prove it. You take sort of hitting set of the first n over 2i vertices. So I take the collection of I tuples that hits the first n over 2i things, and I claim that if you do some calculations, you can show that this gives a lower bound to beating this type of concentration. Okay, I'm not going to show this, but the point is roughly, this is the correct answer. We should be aiming for e to the minus epsilon squared K over I. Any questions about that?
For some x, we have to find an x for which it works.
Right. So So now the main question has become: can we find a sparse x which satisfies these properties? For all I less than or equal to k, we want it to satisfy essentially this bound. So find sparse x satisfying this sort of what I'll very informally call degree I concentration.
Font size.
Sorry.
Increase your font size.
Right bigger.
Right bigger. Font size. Got it. Thank you. Okay, I do want to briefly go back here. Maybe I shouldn't.
Do you want to take a 5-minute break?
Do people want a 5-minute break? I'm fine, but
Yeah, it's always the speaker's decision.
Yeah, sure.
okay. No, I'd rather keep going, I think. There's sort of one more thing I want to point out over here in the agreement testing world, which is sort of I've motivated this. Okay, we've said independently, maybe this is an interesting problem. I believe it, or he believes it. Maybe you should too. But if you don't, then you care. And you care about hardness amplification, where this is coming from. You might have noticed that there's sort of something off. I told you the delta, the soundness that you can hope to get, sort of should correspond to this concentration, because we're exactly looking at this K versus I versus K graph over here.
Can I ask you a naive question?
Yeah.
Take I equals,
Oh, sorry, can you?
take I equals 2.
Yeah.
This is something analogous to sampling from a polynomial of degree 2, roughly.
Yeah,
right?
yeah.
Usually when you sample from a polynomial of degree 2, you do not expect to get some Gaussian bound. You should
You
get
get
some
like root K.
exponential. You should get not epsilon
Right.
squared, but epsilon. Why are you getting epsilon squared here? This is a little bit surprising.
Like you're expecting to get like e to the minus epsilon root K?
This I don't know, but I believe.
I think that's roughly what you would expect.
Or is this only true for epsilon less than 1 or something like this? Is this a small deviation bound? Is it a large deviation bound?
No, I think we should think of this as epsilon less than 1.
Okay, then it makes sense.
Okay, yeah, let's say
Large epsilon, right? I wouldn't expect it.
yeah, no, you're totally right.
These are bounded functions that we are looking at. right?
Yeah, so actually, right, sorry, it's trivial beyond epsilon equals
Oh,
1.
yeah, still, I mean,
Yeah.
I wouldn't expect it then, I mean, whatever the correct scale is then. Beyond epsilon is 1 over.
It should not scale like this.
Well, I'm thinking of an example of a set A, which is just take a set.
No, because there should actually be some like division by the, expectation of the function here. So then it would scale with epsilon, right?
Oh, that may be.
I think.
Maybe there's some trick.
I'm ignoring this density. So I think it should scale with this and that would maybe cancel.
No, but that would have been true even for the linear functions case, so that can't be the thing that distinguishes.
So the example.
Well, Chernoff does have this overview.
You need like a maximum perhaps, if it's unbounded.
Yeah, maximum.
Yeah,
Because then the deviations are just controlled by like taking the largest element. So this is a different behavior.
yeah, let's just focus on,
No, I'm not sure that's the right scale. I mean, the example I have in mind is take a set B that's just a subset of N. And then take the set A to be the set at both points in T, R and B. Does that make sense?
no, sorry. I didn't follow.
Induced on a set of vertices, all edges touching.
Okay,
Just the A is the set, right? A is a subset of sets T of size 2. So
Okay.
just take A to be the set of those T's of size 2, such as both elements of T are in B.
okay,
It's just a subset of A. That's a kind of typical situation where you expect some exponential behavior. Because then it's like taking the square of the central limit theorem, right? If I take, random variables epsilon I times epsilon j and I average, right, I really get the square of the Gaussian, not a Gaussian.
yeah.
Epsilon squared is a worse bound than epsilon, so.
For small epsilon, but not
For
for
small
large
epsilon.
epsilon, but not for large epsilon. That's why I was wondering.
Yeah, so-
This epsilon, we fix small epsilon, below
Yeah,
1.
that's.
Yeah.
Yeah, I'm actually not sure what it should look like in this big epsilon regime. Yeah, we typically think of epsilon even as just being a half or something, as some small constant. Small constant less than 1. Within this framework, not
Maybe
in.
like 1 over square root n or something. Oh, okay.
No. it's-
No, it definitely should not be 1.
It's a constant.
That would be like a trivial n in the number of vertices. That would get you nothing.
Number of samples, what is the number of samples? K? Maybe
K.
the square root K.
Well, then this would still be trivial. So,
One difference here is that I think the scaling, the ambient scaling, it seems to be tied down to the max value of the functions.
Yeah.
As opposed to, Ramon setting where it would be to the standard deviation of the function.
Yes, definitely.
In this case, like the scaling is really max. Max is 1 and you're talking.
Oh, okay, so it's I see, so this could be a very bad bound, this probability is small.
Right.
yes.
Because the polynomial is
Yes.
very small.
Yes.
No, then, at that scale, everything's Gaussian, right? Yeah. So, all right.
Well.
All right, well, let me go on because I'd like to at least do one, prove some version of this. I was gonna say one more thing briefly, which I think is another motivation for looking at this, and then we'll actually start proving this. Okay, so I said, this delta in soundness should be corresponding somehow to this concentration. And the thing I want to point out is that this is like not quite what you would actually hope for, right? In the sense that, let's look again at this test, or maybe I actually do this a couple times. There's some issues with doing it with 2, but say you're only testing intersections of size I, then the best possible delta we can get over here is like 2 to the minus I. Why? Because if I pick a random function, it's going to pass this test with probability like 2 to the minus I, right? I look at the intersection, I assign each of them randomly, they'll agree with like probability 2 to the minus I. So if my intersections, if I'm looking at this like k versus I versus k graph, the best possible delta is going to be like 2 to the minus I. On the other hand, this bound sucks when I is large, right? If I is like k over 2, this becomes basically trivial. And in fact, there's like some constant in front of here where it really does become trivial. So somehow in this world over here, we're not quite getting what we want because we're sort of getting a bound that's like, you know, the maximum, sorry, increase font size. Sorry, I guess no, I do mean maximum. And, you know, this sort of balances out at 2 to the minus root k, right? I set I to balance this. And indeed, in this original paper of Bobby and Russell and Valentine, they use this to construct PCPs of soundness 2 to the minus root k, whereas parallel repetition would get you, you know, you want it to exponentially amplify. You want 2 to the minus k, not 2 to the minus root k. So somehow I was telling you the story about how concentration should get you, you know, the soundness that you want over here, but that appears to be not quite true. And this was fixed in a later paper of Aritz and Deneur and Livni-Navan. Had this beautiful paper. Bear with me, there is a payoff here. I think it was 17. And they used, instead of sort of concentration, they used this very interesting analytic inequality called reverse hypercontractivity. It's a property of, again, this sort of K versus I graph structure. Think of now in this case that I is like, you know, I is K over 2. So we're looking at two K over 2 sets intersecting in K over 2. And they use this property called reverse hypercontractivity. And I'm not going to go, you know, deeply into exactly what this is. It was first proved by Barl, and then later, in sort of the context that I'm going to say, it was introduced by, I'm trying to remember, Mosul, O'Donnell. Let me actually look at my. No, it's a different.
Something I remember.
Sorry. Mosul, O'Donnell, Regev, Steif, and Sudakov.
Okay, Morse, I told you. Morse.
Yeah, Morse is right. Yeah. Okay, I guess you would know about the paper.
They didn't remember the names.
No, I didn't either. I wrote them down yesterday. And this property is basically like a small set mixing type property. It says, look at sort of the graph generated by this. Right, so what do I mean by this? The vertices of the graph are the k sets of n choose k, and I draw an edge between two k sets if they intersect in k over 2. Right, this is called the generalized Johnson graphs, I guess, if you're familiar with this sort of thing. And they prove the following, you know, property of these graphs, roughly speaking, that if I take any sets A and B that live in, let's say xk, so this is for the complete, this would be an n choose k, and the density of mu A and mu B is at least like an inverse exponential in dimension, then there must be many edges passing between A and B. That if I look at this graph, and I have set A, and I have set B, then the number of edges that pass between here should be somehow roughly proportional to the size of A and the size of B, which is, you know, what you would expect on an independent or random graph, right? And, you know, in particular, really the guarantee is it says when I draw an edge, you know, SS prime, so these are two k sets that intersect in a k over 2, you know, the probability that S lands in A and S prime lands in B is greater than or equal to the measure of A times the measure of B to some O of 1 polynomial. So as long as the sets aren't, you know, way too small, and notice this is necessary, right? Because if I take, you know, coming back to this diagram, if I take all k sets that live, you know, I take A to be all k sets that live in the first half of the vertices, and I take B to be all k sets that live in the second half of the vertices, you can clearly never go between these two, right? You can't have two k sets in these that intersect at all, so there can be no edges. And this is roughly of size 2 to the minus k. So this is sort of saying that this is extremal. If my sets are bigger than sort of this trivial bound, I must have many edges going between. And
What is x of k here?
okay,
So this was the power.
let's replace this with n choose k, but you know, you could ask for this property on any k uniform hypergraph.
What are you sampling from here?
So
This is two k sets This is the edge in the Johnson graph. It's two k-sets that intersect on half their vertices.
Okay, uniformly then.
Yeah, uniformly at random, but okay, when we move to general hypergraphs, you really want to think about this. As I look at this, simplicial complex diagram, I pick a k-set, I move down to a uniformly random sub k/2 set, and then I conditionally draw another k-set, conditioned on containing these k/2. That's the graph. When you're n choose k, it's all uniform. But if we were doing some general x, we want to prove the same result on that. Okay, so they use this to prove, this type of small set mixing up to this e to the minus k to actually prove, e to the minus k soundness and sort of match combinatorially parallel repetition and get these this sort of near optimal hardness amplification.
But hang on, are you claiming that the analogous statement is actually true for any xk?
No.
Okay.
It's definitely not true. And in fact, this is sort of like this is closely related to what's called having a modified log Sobolev inequality. It's not exactly the same, but you can't have modified log Sobolev in a sparse complex because you can't have hyperfast mixing in a sparse complex. So it's easy to think it might just be impossible for this to hold in a sparse complex. Luckily, Yotam and I didn't know this. And it turns out it's not true, that you actually can have reverse hypercontractivity in sparse complexes. And moreover, how does this relate to the story of concentration I was telling you about? It turns out concentration implies reverse hypercontractivity in this, at least in this setting. Let me just write this, and then we'll actually prove move to proving these concentration bounds. So here's a theorem, which was, I guess, really our original motivation in this from this work. It says, if x, and then I haven't defined this yet, but if x and all of its local components, what are called links of x, which I'll define in just a second. So if x and its sort of restrictions, its links, satisfy this like e to the minus epsilon square over k over I. Really, the epsilon's not important, just this k over I concentration. This actually implies reverse hypercontractivity. At least in this small set mixing formulation.
That's bound that you know.
It implies this bound.
Yeah, because reverse hypercontractivity, well, reverse hypercontractivity is a stronger state, right? It's a restrict contraction.
Yeah, so
Okay,
right.
you know.
So you can transfer this over to a statement that looks more like reverse hypercontractivity, except it has a constant out front.
Exactly. That kills the connection.
Yes, that kills the connection with MSI. Yeah, good. Right, so when we move to general function, this is like the Boolean function version. When we move to general functions, you'll lose some, like, there'll be like a 2 outside of here, and that actually means you don't contract the norm for all, yeah.
Which you don't care about.
Which I don't care about. Yeah, I don't care about it too, but in like traditional reverse hypercontractive inequality, you would care about it. And yeah, then it probably is impossible, I would guess. But because we don't care about the constant, we're totally fine. We can get this. Okay, I want to actually now prove at least the Chernoff bound for HDX and maybe tell you about how the lifting to general I goes. Any other questions before we move to that?
Sorry, what does it say mu is at least mu A mu B is at least.
Oh, this is at least like inverse exponential. The densities are at least 2 to the minus k. Right, it's, think again of this counter example that says, there exists 2 sets of size 2 to the minus k such that they don't intersect in any vertices at all. So like, clearly I have to have some sort of assumption like this.
I just couldn't.
Yeah, sorry. Yeah, that's a bad board to write on. Okay. Yeah.
Your condition here, do you really, so you need to really check like every link and then you check this property for every I?
I mean, I don't know if it's necessary. In our proof, the way that it works is you inductively, like you want to say some statement about k over 2 versus k, but you can't because this concentration bound is bad. So instead you draw a k over 2 set by drawing it in small portions. So I draw the first 5 vertices of it, and then I induct locally conditioned on those 5 vertices, and then I again apply that, each time getting e to the minus k, and I'm building up this k versus k over 2 versus k thing. So in this case, in this proof, I really need in each step that I locally satisfy e to the minus k over I. Whether that's actually necessary, I don't know. It's just how the
Do you
proof
know,
goes.
for example, whether or not it would be plausible to just check this condition for the stream links, like size 2, I guess, or
Like the links at the bottom, like the
over-
links of vertices
yes.
or something?
Or edges, I mean, yeah.
I don't have a counterexample.
Well, there's a,
With the HDX, whatever property of the
Yeah.
complex, by definition, it is inherited by the link.
Yeah, it's,
So you don't have to worry.
but it's interesting, maybe some object is not an HDX could
Yeah.
satisfy
Yeah.
this.
Yeah.
or.
In an HDX, it's for free because the conditionings of an HDX are an HDX.
Oh, okay, then, sorry, I missed that. You're saying HDX is just give you this property. I didn't realize that, the sampling property.
Well, yeah, because I haven't stated the
I see,
theory.
okay.
This is true. I haven't even told you what an HDX is. Okay.
Just clarify what you're, in this theorem over here, what distribution are you sampling S and S prime?
It's this, I draw a K set, I uniformly at random subsample a K over 2, and then I conditionally complete it to a hyperedge containing the
So
K
it's still
over
that
2.
distribution, even though that's not the sampling procedure that you described that happens in the proof.
Yes, no, it is you can equivalently do this. You can flip this distribution. I can first sample the K over 2, and then independently sample the 2 K sets. That's the same distribution as going, I'm just marginalizing differently.
But you said you sample 5 vertices at a time or something.
Yeah, so I can draw a K over 2 set by first drawing the first 5 elements of it, and then conditionally the next 5 elements of it, and conditionally the
Oh, I
next.
see.
So it's the same distribution, I'm just drawing it part at a time.
That's the distribution basically of the intersection of S and.
Yes.
And then you just conditionally those.
Then you just independently, so each time you say I sample well, and
Okay.
that's how the proof goes. Yeah. Okay, but we're not even like close to reaching that point, okay, I'm gonna skip some exact details here.
You can use that part if you want.
No, I wanna save that, because it'll be used in the proof.
Okay.
So I'm gonna instead erase this. Maybe it's a mistake. Let's see.
You're gonna prove to us the result that we already know for Thunderwalk?
No. So, okay, the first thing I wanna say, so our main question is find a derandomization, right? Find sparse. The first thing that I want to show you is, okay, well, maybe we should try Expander-Chernoff that worked for I = 1.
Oh,
Now I want to claim this is gonna fail as soon as you go to 2. The K versus 2 concentration in Expander-Chernoff fails, so we're gonna need to do something else. So I'm just gonna sort of morally write this, I won't fully prove it to you for lack of time. So, what does this Expander-Chernoff complex look like? Each of these guys is some length K path in my expander. And the key thing here is, let's say we take an expander that has no short cycles, right? Many constructions of expanders don't have short cycles. If I were to fix, how am I generating X2? I'm taking a random pair of vertices in this path. And, with constant probability, this pair is probably like reasonably far apart. And on the other hand, if I fix this pair of vertices, there is only one path going between them. So it fixes this entire subsection of the set of paths that contain, these 2 vertices. So the point here is that sort of X2 versus XK doesn't look pseudorandom anymore at all. I've fixed like a huge portion of my walk. And indeed, you can use this to build a counterexample to sampling. Maybe I'll just mention it very briefly. All you do is you pick some subset of sort of marked vertices of maybe size like n over 2, take like a 1 over 2k fraction of these, and your function, I'm cheating a little bit. I'm gonna sort of flip instead of drawing a guy here and seeing if it samples a set down here, which is what we've been doing, I'm gonna flip the sampling guarantee and say there's gonna be a set up here. I'm gonna draw a guy down here and see whether it intersects up here. You can move between sampling guarantees of, this direction versus this direction and this direction versus this direction. So for the sake of a lower bound, this is sort of sufficient. So I'm going to take all paths that have, a marked I'm gonna, all paths that have a marked vertex will be the set that I'm looking at up here. And the point is that, roughly, how do I draw a pair? I draw a random guy here, and then I subsample 2 vertices. So if I draw a path that, you can show about a constant fraction of these paths are gonna have a marked vertex. And let's say for simplicity, the marked vertex appears sort of somewhere in the middle. This will happen with reasonable probability. If I now subsample my 2 guys to be, across this marked vertex, then all of the paths that contain this pair are marked and therefore have value 1. So that means with at least constant probability, the neighborhood of my guys here is entirely contained in this set T of marked guys. Right? So with constant probability, my local density is just 1, but this has some, density like 0.8 or something. So with constant probability, I have a, constant fraction sampling error. So, whereas we somehow want like epsilon versus e to the minus epsilon squared k over 2 here. So we're very, very far from, this sort of totally fails sampling. Okay. Great. Okay, so what sort of went wrong here? What went wrong is that when we conditioned on some subset of vertices being in a path, being in our hypergraph, that the pseudorandomness sort of totally broke. And so inherently sort of these, despite the k versus 1 bound working, these are really inherently low dimensional objects, right? I'm taking some walk on a low dimensional graph, and this somehow exploited this fact. So the idea now should be, what if instead of looking at expanders in 2 dimensions, we really tried to build a high dimensional pseudorandom object. In particular, an object that's pseudorandom not just sort of globally, but even when I condition in the object. And as some fraction of the audience knows, these objects exist. They're called high dimensional expanders. And indeed, the modern spectral definition of high dimensional expanders was sort of introduced exactly in this context. So let me write a theorem. So I'll define HDX for you in just a second. Here's a theorem of Derandomization and Hopkins. So if, X is what I will define soon, sort of a sufficiently good high dimensional expander, then I'm not going to write out the whole probability, but right, it's this k versus I concentration. So you get sort of k versus I concentration will be roughly I over k epsilon squared. So you're getting like an inverse polynomial or a sort of Chebyshev style bound. And of course, we hope to get Chernoff. But this was still very powerful. This allowed a lot of this agreement testing stuff to go through. And we'll hear in November about turning this sort of thing into actual PCPs. So even this is very, very powerful, but it doesn't actually answer our question, right, of getting this optimal e to the minus epsilon squared over I. So the theorem that I'll prove to you in the last 40 minutes is the following adjustments to this theorem, which fixes this fact. This will be e to the minus some constant epsilon squared k over I, and maybe there's some constant like 1 over epsilon out front or something like this. So we will show these, and maybe I should say that like, what's the density of the objects we get here? I think the best possible thing we managed to get in the paper is like the size of xk is roughly maybe n times 2 to the k cubed or something like this. So the density is a bit worse than expanders, which remember was n times 2 to the O of k. But now we have all this k versus I, reverse hypercontractivity, agreement testing type stuff. Okay. So I want to actually define what HDX, etc. are for you and prove at least the I equals 1 version of this theorem, and maybe tell you. Well, first I'm going to prove I equals 1, and then I'm going to argue you can lift it to.
Yeah, but I equals 1, isn't that what we already know for expanders?
I equals 1 we already know for expanders, but that doesn't mean that a high dimensional expander's k faces are not a walk.
Agreed. It's just
Yeah.
to.
Yeah, so this would not be useful in and of itself, I guess. You could just use expander walks, but the way we'll actually prove the I bound is we'll prove it for 1, and then we'll basically do exactly what I explained up here for the complete complex and look at partitions argue this is an HDX and lift to k over I.
Even the I equals 1 case wasn't known with this exponential.
No, as far as I know, it was.
So the only cases where we had this exponential decay was for walks and expanders.
No, I mean, there are other samplers you could.
Or any other sample.
We did not know that high dimensional expanders, which, you need other properties of HDX and various things. We didn't know that these satisfy sub-Gaussian concentration, as far as I'm aware.
X is the statement that if X is any HDX, or is the statement that you can construct.
Any
X?
HDX. Yeah. Of course, there should really be some dependence here on how strong an HDX you are, and hopefully I'll get to that. But, for sufficiently strong notion of high dimensional expanders, we'll get this back.
But
You
so
mean
is
that
this
the
two,
lambda should.
Yeah, the
be
lambda, yeah.
is this 2 to the k cubed, then just a restriction on how.
That's the best known construction.
HDX.
Yes.
Not for your theorem. If somebody came up with an HDX which improved that, then it would.
Yes.
Okay.
Yes. This is like a 2 to the k field size Romanutian complex. Yeah.
So it's field size to the k squared is really what's written
No, field size 2 to the k.
there. What is 2 to the k cubed come from? Yes.
The degree of a Romanutian complex is field size to the k squared.
Right.
So if field size is 2 to the k, this
2
is
to
2
the
to the
k.
k cubed.
Thanks.
You could also have a much weaker field size and then take a skeleton, and that will also get you this bound, but it turns out that's 2 to the k to the 4th, so it's worse to do that. Anyway, you can play with these parameters and get different. But yeah, this is true for any strong enough HDX, and even I hope to say the weakest possible HDX will satisfy, some will maybe have a root there. You'll still get something very strong, but you won't get fully sub-Gaussian type concentration. Okay, so let me define HDX. Hopefully we'll be able to do it relatively quickly. Could people on the edge could not really see this board. Should I just do the middle?
Just the very.
Just the very edge?
Yeah, otherwise.
Okay. So I'm gonna go relatively quickly here, but please, still stop me if you don't understand something. So when is X, we'll call lambda high dimensional expander. Okay, so, taking motivation from this expander walk case, what did we say? We sort of one, we want X to be a globally pseudorandom object in some sense, similar to expander walks. And 2, we want to still be pseudorandom even when we condition on vertices. And that's sort of our guiding notion. And so for this conditioning, I want to introduce the following definition, which is the link. And this says, so maybe again, let me say, X is now this simplicial complex, right? We've taken a K uniform hypergraph and we've downward closed it. We have K sets, K minus 1 sets, etc. There. So a link, if I look at any sort of subface, in some I tuple that appears, basically the link is just the conditional distribution, conditioning on tau appearing in the hypergraph. So really this is X tau is defined to be S in X such that tau union S is in X. Okay, what does this mean? Let me sort of draw it as a diagram, a little bit more clear. So if I have this sort of xk, xi, and vertices, I'm looking at a particular, I face tau, and to define the link, I'm looking up first at all of the k sets that contain tau, and then I'm removing tau from them. Right, so this gives me a lower dimensional, a k minus I dimensional local simplicial complex.
So the S is an X without tau.
So this is like, okay, T union, I look at tau, I look at all the T union S, and then I remove tau.
Where does it say you remove tau?
So is it X of T in the definition? Just T union S and X of K rather? Or it could be.
No, this is any face whose union with tau is in X
Okay. So for example, if S,
Am I supposed to take something disjoint or something? What is the?
well, if S equals tau, you haven't removed tau, but it's still.
Okay, sorry, yeah.
Right? So it should be X, but with tau removed or something.
Yeah,
You can have the empty set if you want.
you do want the empty set.
No, but you want to remove tau
You want to
from.
remove tau.
S
so
minus tau.
S.
Yeah, okay.
So instead of S minus tau, such as S is an X, and tau doing S and X.
How much effort now it has to go through?
Oops. I'll do this in a second. Okay, good point. This should be S without tau. Thank you.
Such that S is an X, tau units.
Such that,
No, S doesn't
Well,
have to.
then S is an X, that's it.
okay, we'll just, look at the diagram. It should be clear, right? We fix tau, we look at everything that contains tau. And then we essentially look at the marginal distribution over the rest of the variables. Okay, is it sufficiently clear? I lost my notes.
There is a.
Set of all S that contain tau.
There
That's
is
all.
a device that allows you to.
I'll just go without my notes. It should be fine.
I'm sorry, and it's X and not X of K. It's just unlike the.
Like this is X tau,
Sorry,
this is,
T union S.
this is an Xi,
Sorry, yeah, neither of them.
Not here.
Last X, same line,
this X.
yeah, that's X.
Yeah, because I'm defining this not just for the top level. So I could define it for just the top level faces and then downward close it,
Yeah,
and that would give me the same thing.
that's perfectly fine.
Okay, yeah. Sorry, is the definition of a link clear? I think really distributionally, to me, it's easiest to think of it as I condition on tau appearing in the hypergraph. I look at the rest of the variables that then show up, and I marginalize over those variables. That's exactly what is happening here. Okay, that's the link. Sorry, I tried to go faster and then it was slower. Okay, hopefully that's clear.
Audience is doing a great job, I have to say.
I agree. Okay, so now we can define an HDX. So X is a lambda high dimensional expander. If what? If the one skeleton, i.e. the graph, or just forget everything above edges, right? Just look at the vertices and edges, X1 and X2. So X1, this graph, X1, X2, should be an expander, is a lambda expander.
0x1.
No, I'm using the convention that K is K set, and so zero is the empty set here. Yeah, I'm a CS rather than topology. I hope Alex doesn't listen to this. Anyway, so this is sort of my global expansion condition. And then I said, what's our guiding motivation? You fix some subset of vertices, you should still be pseudo-random. Okay, so I also want in every link to have this, this property. So if I look at the one skeleton now of any X tau, I guess I should say two skeleton in this case. This should also be a lambda expander. Okay, and in fact, somebody's probably going to point out, this is just the tau is empty set condition. So really you just say all non-trivial links until there's only two dimensions left should be lambda expanders. That's the definition of a high dimensional expander. And the hope is that we're going to avoid this counterexample that happened with expander blocks, because even when I fix things, I'm going to remain pseudo-random in some sense. Okay. Are people happy with the definition of a lambda HDX? Okay. So now, yeah, let me actually prove the Chernoff bound. Did I also drop the eraser? Let me remind people quickly how the standard proof of Chernoff goes, which is just like bounding the moment generating function. Right, so we'd like to prove. So this is now just over n choose, like I'm gonna fix x and n choose k. And then we're going to see how we have to modify the proof when we're on a high dimensional expander. Right, so the probability over S drawn from n choose k, for some fixed set, fix some subset of the vertices A like we were doing before. So I'm gonna rewrite this as the probability. I'm just gonna do the upper tail. You can do lower tail. Similarly, the probability that the intersection of S with my set A is, more than the mean, is off from the mean of A mu by more than epsilon times K. Here I'm renormalizing things. You say that, for all r greater than 0, the proof is exponentiate and then apply Markov, right? So this is going to be equal to the probability that e to the r s intersect A is greater than e to the mu k plus, r mu k plus r epsilon k. And now I'm going to apply Markov. Right, and this will say that this is at most the expectation over, draw bigger, and choose k of e to the r s a divided by e to the r mu k plus r epsilon k. But now the point is that we want to bound this upper expectation. This is all very standard. So let me sort of rewrite this. Right now I'm writing as S is being drawn as this, K set from this hypergraph, but we can also think of S as being like V1 through Vk, right? So let me go back over to this other side. So actually, I'll just rewrite it here. So we can view this as like, expectation of V1 through Vk being drawn from and choose K of the product of e to the r indicator of A with e to the I, right? This is equivalent. The number of S that intersect with A. I'm just taking e to the r 1 if my vertex is in A and 0 otherwise. The point is that these are negatively correlated random variables, so I could pull this product outside of the expectation. This is the standard proof. So this is now less than or equal to, each of these inner terms is the same. So this will just become the expectation of e to the r 1a of v, where v is drawn, is a uniformly random vertex to the kth power, right, which we got from pulling out the product. Okay, well, good. Divided by. Some people look confused there. E to the r mu k plus r epsilon k. I'm using negative correlation. Yeah. So that's the step that's going to break in an HDX, and the whole point is going to be prove some version of this inequality. But just if people haven't seen this in a while, I want to give a refresher. Okay, now I'm not really going to do the rest of the proof, but the point is, I approximate this as 1, e to the x as 1 plus x squared, which allows me to move from 1a to the density of mu, and then I pull it back to e to the x. So I'll sort of use like 1 plus x less than or equal to e to the x less than or equal to 1 plus x squared. Go through it in your own time if you want to. This will imply that this is like less than or equal to e to the r mu k plus r squared mu k over e to the r mu k plus epsilon r epsilon k. And now these terms cancel and we're left with this r squared mu k over r epsilon k, and I can set r to be like theta epsilon or maybe even epsilon over mu if I were really doing this tightly, and this will imply this e to the negative epsilon squared. Maybe there's like going to be a constant or something.
You're using that epsilon as small.
I am using that. Yes, I am using that epsilon as small.
E to the x less or equal 1 plus x squared.
Right. This will only be true. Yeah. Good. Yeah. In fact, even I was looking at some other proof, and this is what broke. Also, good. So I am using the fact that epsilon is 0, 1 exactly here because this is like true for x in 0, 1. Okay, that's the standard proof of Chernoff. So, what actually breaks when I replace this with a general hypergraph? Well, the only time I actually used the property of the hypergraph was this negative correlation step. And, unfortunately, HDX are not negatively correlated. That's way too strong of a condition, but at least I have my guideline. I want to prove some version of this inequality, just using this notion of lambda HDX. Okay. Okay. So let's repeat our goal. Now we do the same proof up to this point here where I need to bound the moment generating function. So we want to show that the expectation, so now S is going to be drawn from an HDX, the K phases of an HDX instead of n choose K. E to the R S intersect A is at most some outer constant C that's going to correspond to some loss that will, be based on the expansion of X.
I thought that A was a subset of the I phases, or you're just taking.
No, the vertices. We're just doing I equals 1.
Oh, now we're doing I equals 1.
This is I equals 1. So this is just Chernoff, like standard Chernoff. Afterwards there was, I said, how do you get K versus I?
Okay.
You do this random partitioning. So we'll lift Chernoff at the end to be K versus I. So for the moment, sorry, I should have made this explicit. We're doing I equals 1. So there'll be some constant here out front. And then we wanted to get, the expectation of the vertices over x1 or just n. That's basically the same thing that we had above of e to the r1a to the k. Right? If we could prove this, we'd be done. I'm just going to do the exact same calculations I did here, and we'll be fine. So this is really the meat. Okay, so I can't apply negative correlation to prove this. How am I going to do it? Well, I'm going to try to set up a recursion. What I'm going to do is I'm going to draw S, S is equal to, V1 through Vk. And what I'm going to do is sort of draw the first half of the vertices and call this S1. And then conditionally, I'll draw the second half, of the vertices. So I'll write S is equal to, union of S1 and S2. And I'll try to split the moment generating function, this guy into the product of expectations across S1 and S2. Then these guys are sides K over 2, and I'll recurse, right? It's like an induction, I'll apply the inductive hypothesis. Okay, so I'll take this, forget this left side for now. Right side. So this guy, this is equal to, from what I just said, I can draw S1, union S2 in this manner. And this will be e to the r S1 intersect A times e to the r S2 intersect A, right? So the exponentials add up. And now what I want to say is I want to view this as drawing an edge in a certain graph called the swap walk, related to this complex X that I'm on. So what does this look like? Over here, I have xk over 2. So I have my family of k over 2 sets, right? That's where S1 and S2 are coming from. This is why I didn't want to erase the other board.
S1 and S2 are equal.
It's right here. I'm just redrawing it, but now this is xk over 2. Yeah, sorry, what did you?
S1 and S2 are equal sides.
Yeah, these are both k over 2s. And actually for our proof, it will be important. I don't know how to do this with not equal sides. So I'm just redrawing this diagram, right? So now we have S1 and it's connected to S2 whenever S1 union S2 is a K face, right? So basically these have to be disjoint K over 2 subsets, otherwise they wouldn't be an XK, whose union is a K face. This turns out to be a very well studied and very useful graph on high dimensional expanders. And for intuition, if X was the complete complex, this would be the Kneser graph, right? Which we know has very, very good expansion. So we would hope that, if you take this notion of high dimensional expander, that this graph will also have good expansion. We'll have a small second eigenvalue. So for the moment, I'm going to call this graph, if I instead put J2 j on both sides instead of k over 2. I'll call this Sj, and I'm going to call gamma j to be, the second largest eigenvalue of this. Okay. So the point is that I'm now going to apply spectral expansion. I'm going to go back and I'm going to say we have exactly this situation, right? We have the expectation of f times g. They're the same function in this case. I can use spectral expansion of S of this graph to split this into expectation of f times expectation of g plus or minus, lambda in their variance. Okay, so I'm going to apply this. And, these are actually the same function. They're just of, S1 and S2 sets. So what I'm going to get is the expectation now over T drawn from xk over 2 of e to the r p intersect a squared, right? That's the expectation term. So hopefully you can see here that we're close to setting up a recurrence. I started this over xk, now I'm over xk over 2 squared. And if I were to get down to vertices, this would exactly be e to the r, 1a. Right? So if I could complete this recursion, I would finish the proof. The problem is that there's an additive error term, right, that we have to figure out how to deal with. So we get this, plus gamma j.
K over 2. J is k over 2.
Yeah. Thank you. J is k over, later in the induction, it's j, but at the moment it's k over 2. Times what? Times let's just say the 2 norm, for simplicity, 2 norm squared of f, right? So this will be plus, this will be the expectation over t in xk over 2 of the square of this function, right, which is e to the 2r t intersect k.
This is how you get the Chebyshev type bound that you mentioned before. It's just one step.
You get the Chebyshev type bound by showing that this bipartite graph between k and I has second eigenvalue about I over k. Which I think is not quite the same thing as this. I don't know, maybe you could also do it like this, but that's at least how it's done in the original paper. You just look at the spectrum of this bipartite graph. Okay, so we sort of have two things, right, that we need to solve here. First of which, what is gamma k over 2? So it's going to have some dependence on lambda. And second, how in the world do I deal with this variance term, right? This seems to be ruining the recurrence. Okay. Better track of erasers. Okay, we've used this, so now I can get rid of it. Okay. So let me write these as two lemmas. So this is a really well-studied graph on high-dimensional expanders, and in fact, I'm going to use a bound from Siki, or this work of Gerlifshitz and Liu. I should say that the study of this was first introduced independently in Deschanteneur paper, and also a paper of Alev, Geronimo, and Tolsiani. And it's been improved several times since then. Even this is not the best possible bound, but it'll be good enough. There was later improvement. And the statement is very simple. It says that gamma j is at most j times lambda. I'm not going to have time to prove this, unfortunately, but you can ask me after, and I can show you how it's proved. The point is the intuition is that if I looked at S1, right, which is just swapping between two vertices, this is the adjacency matrix. This is the one skeleton, right? So this has lambda. If I swap between 2 and 2, I sort of induct on, I fix locally into one of the links, and I sort of just do this inductively, and I pay a cost of the dimension to do this, and I lose a lambda each time I increase the dimension. So I end up with j lambda. It's sort of a lie, but that's approximately how the proof goes. Okay, so that one we won't prove. Here's lemma 2, which I will try to prove for you. And this is this variance term. So I'll mention that in the proof of Expander-Chernoff, you don't do this k over 2 split, but you are still sort of splitting apart the individual vertices, and you show that this term can be related back to this guy up to some loss in the expansion. I don't know how to do this on a expander. I don't know if it's impossible. We couldn't get it to work. What you can show is that this term is actually close to this original term that we were bounding. So you move sort of all the way back to the left side of the recurrence. So let me write the lemma. The expectation over xk over 2 of e to the 2 2r t intersect a is at most e to the r squared k times the expectation of s in xk, so we move back up to level k of e to the s cap a. Okay, does the statement make sense? So we're losing some, factor here that we're going to pick r to modify, and then this is back on the left side of our recurrence. So
Factors are more than one. I mean, it seems useless here, no? I mean,
this factor is what, remember, this is getting hit by lambda. So, coming back here,
lambda times k over 2.
No, lambda sub k over two.
Lambda of k over two.
Lambda j.
well, which is
Rounding it by j times lambda, which would be lambda times k over 2 in this.
yeah, but as we recurse down, it gets smaller and smaller.
No, think of lambda as much smaller than k. It's like exponentially smaller than k.
So if lambda is
Are we
what,
allowed to do that?
yes,
Sounds good.
you can set the field size to be what, this will correspond to the field size that you work over. I can set it to be 2 to the k, I can set it to be
So
2.
this is like you pick a very high degree.
Yeah, I took a high degree
I
expander,
see.
but even if you do the weakest possible thing, I can set r to be 1 over root k. This becomes a constant, and I'll get this e to the minus root k. So that's why when I said earlier that you could do root k to k, that's based on, do I pick this weak high dimensional expansion or very strong?
So the point is, if you want to do this for a very large k, you will have to choose a very high degree expander. Right?
Yeah.
I see.
Yeah.
You cannot choose a single expander unless k go to infinity.
Not to,
I mean, I wonder if
It
even
will be a
for,
constant. It will be a constant.
I think of k as very constant or very slowly, like log n or root log n.
Sorry, this is R? How do you choose?
This was like what, okay, let me, this term is now, lambda times k over 2 times e to the r squared k times this. This was the discussion of what do you need to take lambda to be for this recursion to be solvable or to give you a good bound. But let me just actually write it, and we were talking about it without writing. Let me just actually write it. Yeah, so now we apply these two lemmas. Right, this term becomes lambda times k over 2 times this original left side. Times e to the r squared k times this original expectation. So now, I have a recurrence relation, right? I subtract this off the left-hand side and I divide, assuming that this is indeed less than 1. And, basically I end up setting this recursion, t of k, this original thing, is at most 1 over 1 minus lambda sub k over 2. Sorry, I guess I'll put in the lambda for the HDX. Lambda times k over 2 times e to the r squared k times tk over 2 squared. So I get to this recurrence relation, and now I can play with lambda and r to have this solved non-trivially, right? And in particular, let me just show you two settings, which is sort of exactly what we were discussing. Okay, so if I set lambda to be around 1 over theta k, remember that this is not, as I recurse, this is not getting smaller. This is like always 1 over k, but this term's this is like j. This is always getting smaller. So indeed, you can solve this, and you'll end up, setting r, sort of optimize. R will be set to about epsilon over root k, and I'll end up with a bound at e to the minus epsilon squared root k. Or I could, take my field size of my HDX that I'm constructing to be really large, to take really large degree. So I could pick lambda to be like 1 over 2 to the theta k. And in this case, now, this term basically just kills everything, right? And this recursion basically just reduces essentially to Chernoff, and this gets you, e to minus epsilon squared. Okay. And of course, I can pick things in between, and I can interpolate between these two, and I can also sort of cheat. Like I could take a very weak high dimensional, like a d-dimensional high dimensional expander, and then I could look at level root d instead of looking at d, and then I could sort of, using this bound, I could recover this bound on the skeleton. So there's sort of tricks for modifying things to get, fully sub-Gaussian concentration, but with the weakest possible sense, we don't know whether a high dimensional expander that has parameter about 1/k, whether this is the correct answer or whether e to the minus squared k is the correct answer.
I didn't understand if the cheat part allows you to use weaker lambda or no.
It does, yeah.
So what's the lambda you need for an exponential?
Like truly exponential? If you set lambda to be, okay, now it's whether is it just top links or is it all links? Like think of lambda as being 1 over dimension, and then I take k to be root. I look at the root dimensional skeleton.
Oh, what you mean is you're in a skeleton.
I'm in a skeleton.
That's more like you're instantiating your HDX in some way.
Yes.
Okay.
Yeah. That's why I called it a cheat.
I see.
If you're the skeleton of something, but I mean, you guys did this in the original Chebyshev round too, so. Yeah.
In general, for K complex, there's no limit on how small lambda can be.
I think you can pick the field size to be as large as you want, but I don't know,
No,
Tom?
there's a function of that.
I don't think there's a limit, is there?
Along Mopana, we
Yeah.
talked about it.
Oh, that's what you were asking.
The degree versus
No,
the.
if it's K, the dimension, lambda can be.
Yeah, fixed K, I can pick whatever field size I want, yeah.
No,
Sorry, I can pick whatever expansion, the expansion corresponds to the field size that you use to construct the complex. Sorry, that's a confusing way to say it. Yes, it can be lambda can be whatever you want for fixed K.
it's like in an expander, can lambda
The
be
degree is
anything?
not K.
The degree, yeah.
So the degree will end up being the expansion I pick to the K squared. But at least in modern constructions of high dimensional expanders, it's an open question whether that's the correct dependence or not. Okay,
But so Max, when between these, right, the top one gives you a worse guarantee, but it's much sparser. So computationally, it's cheaper to implement.
it's actually not true. If you do a partite version of this can be constructed in 2 to the k cubed. Sorry, this is cheap. Like this can be constructed in 2 to the k squared.
It's a lower degree, so.
Yeah, I'm sorry. It is true. Yeah.
So if I wanted to achieve a certain accuracy, right, delta, then I could either increase K or I could work with a denser expander.
Yeah,
Which one
but-
is giving us better if I fix the number?
The best, so if you, right, that's what I was actually saying. If you do this, you want to use a partite object with this parameter. That's,
If you do want the denser one at the end of the day is more efficient for you because
Yeah.
you win more in
Yeah.
the.
yeah, because this is going to be k cubed versus like 2 to the k cubed versus 2 to the k squared, but it's root k versus k, so I actually win on the k cubed.
So you really don't want this weak expander. This is not a good idea.
Well, no, you want to prove, something better than we proved. Now, I hope that this is not the best. That's all we can prove, but maybe you can do better. So I have like 5 minutes. Do people want to see how to lift this to the general I versus k? Or do people want to see like the proof of this lemma, which lets the recursion work?
Can you say for the lemma too, is that just true for any complex?
This is true for every complex. I don't use anything about expansion.
If you need 5 minutes for any one of them, do both, each is 5 minutes.
Wait,
Start
what?
with lemma two.
Okay, I'm gonna start with lemma 2. I got lost there, so.
Javi wants to see the other one as well.
No, I
I can show both, but
5 minutes later, if you can do it.
At least I can give the intuition for both. This was very quick to prove. So the idea in this lemma, the second lemma, is sort of to reverse the process that we did above. Right? Before we drew a k set by first drawing a k/2 set and then a second k/2 set. And now to relate, xk/2 to xk, I'm going to draw t by first drawing a k set s and then subsampling t. So I'm just sort of going to reverse the process. So basically, what am I saying? The expectation of t xk/2 of e to the 2 t cap k. So my claim is this is equal to I draw T by first drawing S. And now I draw T uniformly from S. So this will be the expectation of T, and I'll write this as it being drawn from the complete complex on S vertices. Right, it's the same as randomly subsampling T from S of e to the 2r p cap A. And the point is now I'm in the complete complex. So I can apply concentration bounds, morally, this, because this is from the complete complex, it should be very close to, this inner term should be very close to its expectation with very, very high probability. And what's its expectation? Its expectation is like e to the r S cap A. The point is, up to some loss coming from the concentration of the complete object, I basically get to replace this with e to the r S cap A, and the loss is exactly this e to the r squared k term. That's the moral behind how this works. Really, instead, I'll just apply negative correlation in here, and it's a little bit simpler than dealing with the distributions, right? So in particular, if I apply negative correlation, then this is now going to move to the expectation over vertices in S of e to the 2r 1a to the k over 2. This is still this expectation of S. And now I, move e to the x, 1 plus x, 1 plus x plus x squared. And so then, this will end up going to what? It'll be e to the r S cap A plus 2r squared S cap A. This is at most k, right? So I pull out the 2r squared k to the front. And I proved what I wanted, except maybe I forgot a 2 here. Okay. So that's the proof. We draw T by first drawing S. We sort of localize within the complete complex and apply negative correlation. That's the whole proof. Okay. So notice, like as Xander was asking, I didn't use expansion in here at all. And sort of, I guess the hope, I was talking about earlier is maybe there's some more clever way to do this recurrence that uses the expansion in this step and beats e to the minus root k. So I guess I can just say something about how to move to the general I quickly and then finish. I mean, it depends on what you guys want. Maybe I'll just do it here again. While I'm erasing, I'll mention something that I think is interesting. If you really push this bound up here, you can get away with only assuming that lambda at the very top links is like 1 over k minus little o of 1, like 1 over k minus 1 over k squared or something like that. And you can get some sort of quasi-exponential bound. And this is actually tight in that you can construct complexes that are exactly 1 over k by powering graphs together that have no concentration at all. So there's some sort of very interesting threshold phenomenon that happens at expansion 1 over dimension, where up to that point you get absolutely nothing, and then beyond it you get at least quasi-exponential concentration. So this is what I guess I would call the trickling down threshold, when if you know what Oppenheim's trickling down theorem kicks in, it is. But there's this interesting expansion threshold in HDX where below it, it's sort of, you're not a true local to global object, and beyond it you get all these amazing properties. It also sort of explains why it's so hard to construct an HDX beyond this 1 over k barrier.
You still get what you got, just a Chebyshev type.
No, you get nothing. I can construct, or at least I can construct instances where it's arbitrary, like pick any beta for the constant, like 0.99999 chance of missampling. I can make it arbitrarily bad. Because I take a graph tensor power and I put some like function on the vertices that is going to get missampled. I can explain it to you after, but yeah, you can, it's really, you get nothing. It's a very stark threshold. Okay, I am out of time.
Okay.
Do the,
Yeah.
okay. So I'll briefly.
5 minutes.
Okay, 5 minutes. Intuition for the K versus I bound. Okay, I mean, the intuition is really what I said at the beginning, which is how can I draw instead of looking at all possible I subsets of a K set, I'm going to partition randomly partition my k set S and xk into S1, S2, or Sk over I, where these are all I-sized subsets. Right, so these are all elements of xi, and their union, union of these is x. So I'm going to look at this. This actually generates a simplicial or a hypergraph, right? I can generate a hypergraph. How do I generate the hyperedges? I draw a random S. I randomly partition. This gives me a new. So this moves to a new k over I dimensional, simplicial complex or hypergraph. And I also claim, this is known stuff. I claim that if this is a lambda high dimensional expander, then this is an I times lambda high dimensional expander. So lambda HDX. I think this is maybe sometimes called the faces complex.
This follows from lemma 1.
Yeah, this is exactly lemma 1. So this goes to I times lambda. Why? Because the skeleton, if I compare an edge here, S1 versus S2, this is exactly, I erased it, but this is the swap walk graph, right? This is like the union of S1 and S2 is a 2I set in the complex. And so, this guy is exactly this SI graph, and lemma 1 says that this says expansion I times lambda. I just did this at the one skeleton level, but even if I fix links, it's still going to be true, right? This is just going to be the swap walk within a link of X, which is also bounded by I times lambda. Okay, so this new guy is a k over I dimensional HDX as well. And let's assume for simplicity that lambda is like, 2 to the minus theta k, so it's still like a 2 to the minus theta k HDX. So in particular, on this guy, we have Chernoff. Right, we have concentration about e to the minus epsilon squared k over I, because this is a k over I dimensional complex. So the question now becomes, how do I relate? Chernoff on this guy is a little bit, it's not quite what I wanted to bound. Right, what I wanted to bound is this concentration between k sets, and I choose a randomized subset. And here this is a little bit different. I'm like taking this partition and I'm randomly sampling one of the elements of the partition. Okay, I don't have that much time here, so I can't formally go through the proof in details. But here's what you do. You use a connection with extractors. And this is actually not the argument that's in the paper. This came out of some more recent discussion with Russell Pagliazzo and Tony Patassi. Which is, so here's my, let's say I say the next one for now, but it's this bipartite graph. And the point that, what I want to say is that this guarantee that's called being a sampler graph, that if I pick a random guy, for any set A down here, if I pick a random guy, that the probability I'm within epsilon is at most some beta, right? In this case, it's like e to the minus epsilon squared over I, is equivalent to the following statement. Take any set here of density roughly e to the minus epsilon squared k over I, and look at the induced distribution where I draw a random, so this is some set T. Look at the induced distribution on x1 or whatever you have, or xi, whatever you have down here, by drawing a random element of T instead of random element of xk, and then a random neighbor in x1. Being a sampler, satisfying this like e to the minus epsilon squared, whatever concentration, is up to some small factors, almost exactly the same thing as saying that for all possible sets T, this resulting distribution will be within O of epsilon of uniform over x1 in total variation distance. X1 in total variation. Okay, so now how do you do the proof? You have Chernoff over this k over I guy. I'm going to use it, use through here. So I'm going to look at xk on my original guy. I have this set T. Now I'm trying to prove this sort of extractor viewpoint. I have this set T. Well, I can easily embed it into this new k over I dimensional complex by just let's call TF. Let's move to this. This is like the partition complex, the k over I dimensional partition complex.
What's F? What are we doing?
Okay, I was writing F as faces. This is the partition. This is the new complex. I'll call it Y. Y is the partition, the one that's generated by taking a random partition of the
So the vertices of Y are I sets.
Yeah, so the vertices of Y is the I sets of X. So the whole point is that the distribution is the same. The vertices of these are the I sets. And so when we look at it in this sort of extractor view, being O of epsilon close in either case is the same. So what I want to argue is that I'm going to take my set T and I'm going to embed it into Y in such a way that the induced distribution, when I draw from this T of Y on Y1, is exactly the same as the induced distribution if I had started with T on XK and then taken a uniformly random guy over an I set. So the point is now, this is I'm trying to analyze that this is O of epsilon close to X of I, but now this is what Chernoff says. I use the equivalence of sampling and extractors to say for Yk over I, and this sort of embedded set, which is just, if the union of my partition is in T, then it will be in T of Y.
I don't know, is Chernoff really the theorem we're doing? Why is not the complete complex? So why are we?
No, it's not Chernoff. When I had more time, I was going to introduce this as just an epsilon beta sampler, and it's equivalent to move between epsilon beta samplers, but I ran out of time. Yeah, this has nothing to do with Chernoff. This is just like, if Yk over I, Y1 is an epsilon beta sampler, then Xk, okay, I'll write this. If,
So using the fact that this bipartite graph on Y is a sampler.
yes, so if Yk over I, Y1 is an epsilon beta sampler, and okay, I didn't really introduce these, but think of that beta as being e to the minus epsilon squared k over I. This is what Chernoff means. This implies that xk xi, which is the guy that we actually wanted to bound, is like a 2 epsilon 2 over epsilon beta sample.
Earlier you said that the Y complex itself is an HDX, so can't you just apply your theorem on Y?
Yeah, that's how you prove it.
That's how you, okay, so.
Yeah. Well, you have to make sure, I have to do this embedding, right? I have to make sure I start with the set T, I embed it into Y. Now I apply the fact that Y is an HDX and therefore satisfies concentration.
So why do we need to talk about some new objects here, like samplers and extractors?
It simplifies how would you do this without you need to prove this. How do you prove this object?
What you said will only prove the first line, Chernoff for Y object. If I need to get the.
Yeah, how do I transfer to xkx1? Sorry, how do I use the fact that this, so I've used expansion to say this satisfies is an epsilon beta sampler. Now I need to prove that this implies that xk versus xi is close to epsilon beta sampler. I'm doing this by flipping the view to be picking a set over the top level, because then I can easily match the sets.
I feel like this is exactly the thing you hand waved when we were doing it on the computer.
This is exactly the thing that I hand waved when I did. That is correct. Yeah. This is the slightly less hand wavy version of that. You prove the partition complex being a sampler implies the original k versus I is a sampler at a slight loss in parameters. The cleanest way to do it, as far as I know, is to use this view of extractors that lets you match up the sets exactly. Okay. Yeah, I'm over time. Sorry.